So today we are going to discuss about the stresses in beam, also known as the flexure stress, and let us do the theory part first. And let us take beam and beyond the neutral axis. So this neutral axis, we will apply on the way like this. So the beam will bend and do the figure like this. This section is to so let's not it as a be surrounding this part dash and dash. So this will become dash b dash c dash b dash. And the neutral axis remain the same because there are some assumptions right here that the neutral axis remain unchanged and it is homogeneous, isotropic, and elastic. Then we can see the sectional plane will remain intact after the bending moment of the moment is applied. So now from this, let's take another shape called EF. So we can see the EF like over there. There's our E dash F dash. Now here we can see the AB will contract and CD will expand. So consequently, the above strips will contract and the below strip will expand. So as we can see, the EF is below the neutral axis, it will expand. So if we calculate the strain in EF, then what should be the F side? Here we can see it acts like a or bent like a arc of a circle. So we draw a circular section over here like this. Let's call the angle theta. So the distance from this to this will be our radius of curvature. Uh, and let's call this long distance y. So we can see from the formula arc length is equal to theta times the radius. So from this we can see our EF will become theta r, and also we can see the E dash and dash will become theta times r plus 1. And if we remember the formula of strain, we can write simply a change in length that is E dash F plus minus EF over PF, and let us put the values theta r plus 1 minus of theta r theta. Then you can see the theta term is being cancelled out. So we are left over only y in the numerator, and in the denominator we are getting r. So we can say the strain is equal to y by r. Now from Hooke's law, we know strain is proportional to strain, and we can say the Young's modulus is equal to strain over stress over strain. So if we put the value of epsilon y by r, so here we can write like this. Let put this y right here. So this will become y by r, and this division will become y by r. So this is a part of the proof, and other part is the moment part. So if I do a cross section of a beam like this, and if the neutral axis is the dot and dash line, so let us consider a little portion of this section and call the area dA. So if we calculate the small amount of movement, it will be right dA into the distance. So we are getting the distance, this y bar or y simply because we know the moment is equal to force times the distance perpendicular. So here you can see the moment is over a varying force. So we can directly use this formula. We have to integrate or somehow need the help of calculus here. So sorry, I so this will be EF and we know stress is equal to force over area. So we can write like this from sigma df and if we put back the value of sigma or simple stress and we write Ey r here, it turns out to be E by r y square here. So if we integrate the small amount of dl, we get the whole moment and at the values we can do. So y by r is the constant. We are getting outside interval and left to it y squared d. So the term y squared d is simply second moment of area, the second moment of area, or simply moment of friction about the neutral axis. So we can write m is equal to T by r into I. So from this we can conclude by m over I. So this is the main formula which we have to memorize or somehow keep it in our brain so that we can use it whenever we are solving the problem. So now I will discuss two problems. One is from subject pocket, another is from single. So let's solve one by one. Let solve this problem first. That we are asked to determine the minimum height h of the beam if the flexural stress not exceed 20 megapascal. Okay. So we are giving the value of stress, which is 20 megapascal, and we are also showing the cross section of the beam right over here, and which length is width is 80 millimeter and height is given h. And we have to determine minimum value of it. So we can see this is a mixed problem, and it is much of shear full diagram or bending moment diagram problem. Thus, we have to put it back with the flexure formula. So first thing we can do is to determine the reaction of R1 and R2. So first of all, we have to draw the free body diagram simply. It's also written on the paper. I can see clarity. And uniformly distributed load, and the length is our 4. So the distance is this is one from this system. And then also simply um, hence as it is 2.5 kilometer per meter and the total distance is 4, we simply multiply. uh, 5 Newton and with the length you can get on the same point because 2.5 which is 5.0. So R1 or plus R3 must have to be 10 plus 5. It's because solution of going must be 0. And if I do, let's name these points A, B, let's see. And so if I took more at B, so this force will be 0, so positive 15 tons from 1 which will be 1 from 1 to meter. So is equal to R2 times is counterclockwise, so that's why I'm writing on the right side, or you can simply write as negative. Yes. So my R2 comes out to be 5 kilonewton. So from here we can say R1 must be 10 kilonewton. So we plug the values. This is 10 and this is 5. Now quickly draw the shear foot here. For shear foot diagram, we have to draw cycles of so that we can make sure the diagram is perfect. Like this, a little bit helpful. So I would prefer the moment diagram. So first thing we have to do the shear force diagram in the right here. So at A point, there is no shear force acting on this. From A to B, we have to consider the left, just left of B and just right of B. So if we consider just left of B, you can see the uniformly distributed load which was 2.5 kilonewton over meter and the distance is 1, so we can see, and it is acting downward, so to the negative 2.5, and from right we can see a 10 kilonewton load is acted from in the upward direction. So 10 plus negative 2.5, it will be plus positive 7.5, and then from B to C, again the uniformly distributed load is being applied, and for C we have to do the same thing. I'm just doing it orally. If you prefer, you can do it right on the this portion of the paper. So it is also acting in the downward. So 2.5 minus 7.5 minus 2.5 will give 5. So I'm marking it positive 5. And there is the concentric loop 5 acting. So the value is 0. From C to D, 2.5 time it is 5. So it's, it's negative 5. As you can see, the in D point, there is acting a concentric loop. Now we will say the reaction 5. So minus 5 plus 5. So it's 0. Now we click on the box lines. So 0 to 2 minus 2.5 minus 2.5 to 7.5 from 5 0 negative 5. So this is our first value. From sales goes diagram, this is negative, this is positive, and this is again negative. So if we calculate the area, the area bound by the shear force will be the PMD. So this area is found out to be the smaller triangle. 2.5 is out and the base is 1. So half into 1 into 2.5, that comes out to be negative 1.25. And from here is 0. Let's see from the perspective. And this trapezoid here will be half times 7.5 plus 5 times the distance, which is 1, and this comes up to be 6.25. So 1 minus 1.25 plus 6.25, that comes out to be positive 5. And from this, we'll see that comes out to 5. So as it is below the line, so that is negative. So minus 5 plus 5 0. And it is decreasing if we remember the class. Decreasing, increasing, increasing, decreasing. So there is a positive one and there is a negative one. So this is negative decreasing. So a negative decreasing curve, negative increasing. So negative increasing curve is like this. So remember like this parabolic shape curve, and from this you can see the value is increasing. The value is decreasing, but it is on the positive side. So positive increasing, positive decreasing, positive decreasing. So positive decreasing will be like this. From again, we can see the negative increasing, the negative increasing will be this. So this is our trending moment diagram, and it was aseptic. So now we can use the Flexner formula we derived. So sigma by y is equal to m. So sigma is simply equal to memory, and we were given a cross section 80 millimeter and the height was h. So we know the formula of I for a rectangular section is simply ph cube over 12. And from the neutral axis, my y should be this distance or simply h over 2. Since I put it back, it will simply become ph cube over 2. So I want to write the ph square over 6. And we are given the value of sigma 20. So 20 megapascal or simply Newton over millimeter square will become, and we have to see the moment. So we can see the maximum moment on the BMT is 5 and the unit of kilonewton meter. So 5, so we put it back to Newton, 10 cube, and from meter to millimeter, and also 10 cube. And B was given 80 by 6 and simply h². So if we calculate by calculator, we'll end up getting the h is equal to 3137 millimeter. So that is the answer to this problem. And my voice may be low because I'm fasting during this hours. So pardon if you have bothered by it. And that's it for to see another video.